that to set this background, you need to download that picture in your desktop. Then come to the Zoom app. In the Zoom app, you will see the enable video, disable video option. Click that. Over there, you will see that there is a virtual background setting option available. Click that, choose this particular image as your background, and you close it. And this is set. Thank you so much. Good morning, Dr. P.K. Shukla. So kindly unmute yourself.
Good morning.
Good morning, sir. Good morning.
Okay. How can we start our session on session 2B?
Good morning, Dr. Kamlesh Pandey. To join session 2B, you have the option of breakout rooms available at this trip. If you will click the breakout rooms, so there is breakout room option available where there are, yeah. So if you will click it, you will have 2B, it will prompt 2B and 2C. So you can click on join 2B.
Okay, I will try.
Yes, sir. Close क्यों कर?
Hello.
Yes,
Hello.
sir.
Yes, Mohit sir.
Mohit
Yes.
sir, you have closed.
Sir, breakout. Yes, sir. It was only for 30 seconds. Breakout room.
Okay, I have again opened, ma'am. All the rooms
Okay.
are open.
Okay, sir.
I will request all the participants and the invited speakers, please join the respective rooms. Even I will also request the session chair to join the room so that we can start the session at 9:30 sharp.
वो वाली सर यूनिवर्सिटी वाली, ठीक है। कोई बात
ये
नहीं।
अभी पावर आ रहा है इसमें? अच्छा, तो अभी एक्सटेंशन लगा है।
देख लो अननेसेसरी पंखे नहीं चल रहे हैं और इसको थोड़ा तेज कर लो कि लाइट पता नहीं कितनी देर में आएगी।
हेलो, हाँ प्रमोद जी। हाँ बिल्कुल बिल्कुल। हाँ हाँ, मैंने वही वाला पासकोड डाला है और वही लिंक खोला है मैंने, तो मेरे ख्याल से डायरेक्टली हम वहाँ पहुँचेंगे। ठीक है ठीक है, ठीक ठीक ठीक।
आपको मैं पर्सनल मैसेज यहीं से भेज दूँ तो व्हाट्सएप में भेज दूँ किसी का आपका ओपन है
Session 1A, I request Dr. Syahida. Is Dr. Syahida present, available here? Because we are trying to reach out to her. Dr. Syahida. Good morning, everyone. We are going to start our session shortly.
I think Dr. Saida yet to join. She has
Yes, sir.
not joined.
Dr. Mohammad Noor Faiz. He is available, so we will start the presentation with him.
Okay. Dr. Noor. Okay.
Hello, good morning.
Should
Morning.
good
Please
morning.
Good morning, everyone. Welcome to session 2A. Once again, I'm making the announcement. Those who have their presentations in 2B or 2C are requested to join through breakout rooms. There is an option of breakout room available at the bottom of the strip of the app. So on that app, you have on the Zoom app at the bottom strip, there is breakout room available. Kindly click on that breakout room option and join session 2B or 2C according to your own choice, or if you have your presentation over there. So we're going to start our session 2A today. Okay, so dear participants and respected dignitaries that are present here, a very warm welcome to you all to the second day of ICSEM 2021. And the session chair of this session, pre-lunch 2A session, is Dr. P.K. Shukla. And I take this opportunity to introduce Dr. P.K. Shukla to all. Dr. P.K. Shukla received his PhD in physics from Avdesh Pratap Singh University, Rewa, and postdoctoral research from Banaras Hindu University, Varanasi. He has published more than 35 research papers in reputed journals and has participated and presented and delivered invited lectures in several conferences, symposia, and workshops. Dr. Shukla has been reviewer of various international journals of repute. His area of research interests are polymer electrolytes, electrochemical energy conversions, and storage devices, photoelectrochemical solar cells, and semiconductor nanomaterials for optoelectronic application. He is working as a professor of physics in Engineering Institute since 2007. So with that short, brief introduction, I request Dr. P.K. Shukla to session this chair. Sir, please.
Thank you, Vinesh. Good morning to one and all present in this session. Before I proceed with the responsibility given to me, I feel privileged and would like to thank the organizer for providing me the opportunity to chair the session in this international forum. As mentioned in the schedule, in today's morning session 2A, we have a sum of 7 invited talks, each of 30 minutes, and would like to request all of the participants, presenters, that kindly conclude your talk within stipulated time limit of 25 minutes for presentation and 5 minutes for question answer session, so that we can conclude the complete session in the time frame of the schedule. With this request, I would like to call upon Mr. Noor is present. Ma'am?
Yes, sir. Dr. Mohammad Noor Faiz is available.
Okay. I would call
Right.
Muhammad Noor Faiz from Malaysia to present his talk on nanocellulose as novel filtration material of organophosphorus compounds.
Right.
Can I see you, sir?
Yeah, I can see you. So
Oh,
can I share my slide
yes,
on
yes.
screen?
Please, you can share now.
All right. Okay, good morning and hi everyone. I hope everyone is healthy and stay safe during amid of this COVID-19 pandemic. I would like to say thank you to Professor PK Sukla and also to the organizing committee of ICSEM 2021. And I also would like to thank to Prof. Pramod for inviting me for this such a wonderful conference. And today I would like, my name is Faiz, and I will be presenting for my research entitled Nanocellulose as Novel Filtration Material of Organophosphorus Compound. I'm from National Defense University of Malaysia. So I would like to begin with the introduction of organophosphorus. I believe that all of us might really want to know what is organophosphorus is usually used. Organophosphorus is an organic compound that is usually used as a pesticide, and it also been developed as a chemical warfare nerve agent such as soman, tabun, sarin, cyclosarin, and VX. It's highly toxic and very dangerous. I think some of us might even what we call it, some even know that actually we have the organophosphorus compound in our daily life, because usually the organophosphorus are used as a pesticide. Some of us might have the malathion, paraoxone in our store. So this organophosphorus poisoning has been a frequent cause of admission of people to the hospital, mostly farmers. And based on the data reported, about 3 million acute intoxication were reported annually. And I think everyone has heard about the news before. On 13 February 2017, the Kim Jong-nam, who is the family members of the North Korean leader, was killed using a nerve agent known as VX. So the VX also is one of the example of the organophosphorus compound that been used as the chemical warfare nerve agents. So this slide shows that the common equipment used to avoid the penetration of the organophosphorus compound. So there are two major groups of people who are usually exposed for the organophosphorus compound, which are military and also the agriculture workers. So they are using several kind of equipment, as we can see here: the military live straw, the filter mask, and also some of the other equipments to prevent the penetration of this compound. So most of these compounds were made from the special material in order to avoid the penetration of the organophosphorus. However, I cannot say that all the material used for this filter are really effective to filter the organophosphorus. It has still have some drawbacks need to be accounted. So currently, there are the activated carbon has been widely used as a filtration material. We can find it in most of the filter equipment and also a cartridge. It's abundant available, and I cannot deny that activated carbon is one of the very excellent material to filter several chemical contaminants. We should also include the organophosphorus. However, this kind of material also has some weaknesses, drawbacks that we have to be accounted. For example, it has a low specific surface area. So when we use the filter base made from the activated carbon, the filtration cartridge need to be changed frequently. So it makes it difficult for us to use it. Even when we handle some of the chemical experiment in laboratory, when we use the activated carbon filtration, we have to replace it frequently. So frequent, like about after half an hour, we have to change it. So it's very difficult and uncomfortable for us to use the activated carbon for such a long period of time. And it also reported has a costly material where where we want to produce the activated carbon, we have to use the pyrolysis system that require high energy. And it's a non-renewable physical form and also suffer from material losses during regeneration process. And as I said before, it's a heavy and require large volume in filter cartridge. So scientists has been investigated the suitable solution or discover a new material that can offer a good alternative to activated carbon. So the combination of bioabsorption and nanotechnology can be a great potential candidate material for the filtration material of organophosphorus. I think some of us already know about the nanocellulose. What you can see here, nanocellulose is the plant-based material that can be derived from biomass. So it actually is 1,000 times smaller as compared to our hair. So this material, nanocellulose, has several unique properties like high mechanical strength, large specific surface area, renewable and biodegradable, which make it suitable for various applications. As what we can see here, it has been many papers has been reported the successful use of nanocellulose for filtration, military, medical clothes, biomaterial, composite packaging, adhesive, cosmetic, thickening agent, paint, also coating. So in our developed technology, we would like to propose the usefulness of the nanocellulose to be as a filtration material of the organophosphorus. This is because of the unique properties of the nanocellulose, as I mentioned in the previous slide, mainly because of the presence of hydroxyl group, as what we can see here. The presence of OH hydroxyl group here actually is very benefit to avoid the penetration of the organophosphorus. And based on the theory that we try to share here, we can see the chemical structure of these two compounds, organophosphorus and cellulose nanofiber. It has abundant amount of, for nanocellulose, it has abundant amount of hydroxyl and also alkyl and carbonyl for organophosphorus. Actually, these are very benefit in order to form the chemical interaction, which I will be shown later in the next slide, how it can be interact with nanocellulose. So this slide shows the interaction mechanism between the nanocellulose and the organophosphorus compound. I divide it into two, the unmodified and modified nanocellulose. For unmodified nanocellulose, the presence of hydroxyl group here actually can form the chemical adsorption with organophosphorus. The presence of the alkyl here and hydroxyl will get connected by produce water. And we also can modify the nanocellulose by making it positively charged, or known as the cationic nanocellulose. So it has a positive charge here. So it can interact with organophosphorus, which can produce a negatively charged in water. So it can use to absorb the organophosphorus by static interaction. So based on our current research finding, as what we can see here, this is the chemical interaction study by Fdir. We can see that the nanocellulose, after immersed with malathion, is one of type of the organophosphorus that I use in my lab. So we can see the presence of a carbonyl stretch peak here, indicate the successful interaction or bind of the organophosphorus towards the nanocellulose, because only the organophosphorus has the carbonyl functional group, as I presented in the previous slide, right? So, however, for our activated carbon, no changes can be seen for the FDIR spectra here, indicate that activated carbon actually cannot form a good chemical interaction with organophosphorus. It just used to entrap the chemical compound, right? So I also, my team also been studied the absorption capacity. Interestingly, as we can see here, that the nanocellulose has 5 times higher for the absorption capacity as compared to the activated carbon. So it proved that the nanocellulose, without any modification, actually has a good ability to be a material for filtration of the organophosphorus. And this slide also show the example of the other finding that have been proved here, the capability of the nanocellulose to absorb the organophosphorus. We can see this contaminated water in white color, and then I added with nanocellulose for a certain period of time, and then after the water get filtered, we can get the clear water. So I tested for the GCMS of this filtered water. We can found that the organophosphorus can be removed totally from the contaminated water by using nanocellulose. So another interesting that has been found that the nanocellulose can be reusable as the can be reused for many times after being absorbed by organophosphorus. It simply can be seen here. The contaminated water contains organophosphorus, and then when we add nanocellulose and absorb the organophosphorus, and we can remove the nanocellulose and the organophosphorus, and then we can make this desorption process by simply dissolve this material into methanol or any kind of solvent that can dissolve organophosphorus, and the nanocellulose obtained can be reused again. And in terms of the advantage of our technology as compared to a current available material in the market, which are activated carbon, our developed nanocellulose-based filtration material has several advantages. As we can see here, it a renewable raw material, as I said, because it can be obtained from renewable biomass. That, for example, Malaysia has abundant amount of biomass from oil palm, so we can turn it into high value products, and also it reusable, lightweight material as compared to activated carbon. So we don't have any difficulty while using filter cartridge made from nanocellulose, and it has a high performance in terms of the absorption capacity and also mechanical properties, and it also safe to help because it's a plant-based material, doesn't has any health effect when we use it, and it has an affordable cost. And I believe that some people might say that nanocellulose is still expensive as compared to other material. Yes, I cannot deny it, but we believe that a lot of research are currently being carried out, even in our team also. We try to make several alternative or technology to improve the production of nanocellulose, so we can sell it in a similar or lower price as compared to other material, especially the activated carbon. So in terms of application, this technology, the nanocellulose-based filtration material can be applied in many applications for army mask cartridge, army outdoor life straw, water filter material, air purifier, and also especially for farmer protection masks that can prevent agricultural workers from getting the organophosphorus poisoning. So in terms of the market potential, we also evaluated some of the market potential of this technology based on the cumulative annual growth rate. As we can see here, both filter and nanocellulose receive high demand on the market right now, where the growth rate for filter is about 5%, while nanocellulose is 14%. It's a quite new material that received my attention, especially in the developing countries right now. So the total addressable market for filters also very quite high. For filter is about 74,000 billion US dollar, while nanocellulose is 530 million US dollar. And I believe that it keeps increasing time by time. And another point that I want to share here, the development of the filtration material for organophosphorus compound is generally required because as the Malaysia also one of the large agricultural sector, so we have to develop this kind of material for the agriculture sector, not only in Malaysia but also around the world, and also India also can be benefit for this technology, and Malaysia has so many filtration companies where the technology can be transferred, and we also been interviewed several industry players. And we found that several companies have shown the interest to market this product. So we hope that this technology, nanocellulose-based filtration material, can be commercialized soon. So current achievement, we have obtained the IP for the technology and related publications and awards. We got a gold medal in the previous 2020 ITEX. And as for conclusion, I can say that nanocellulose is capable to absorb organophosphorus compound, and the absorption capacity of nanocellulose towards organophosphorus is 5 times higher as compared to activated carbon. And nanocellulose as a filtration material of organophosphorus has a high commercial value. And extensive research are currently being carried out to explore more on this topic. As I said before, today I only present for the unmodified nanocellulose to absorb the organophosphorus, but we can do a lot of things like we modify to make it cationic, or we can discover the parameter for the absorption to be done, like we alter the pH, concentration, the temperature, so we can report the data and publish in the journal. So I would like to acknowledge my team members. Here are my team members: Associate Professor Dr. Nur Azila Muhammad Kasim, Professor Victor Faizal Knight, and also Emeritus Professor Dr. Wan Mazima Yunus. And also would like to thank my research grant who support this research, and also for the university, National Defence University of Malaysia. So with that, I would like to thank you to everyone.
Okay, thank you, Dr. Noor, for nicely presenting on nanocellulose as novel filter materials. Now the session is open for questions and queries, if any. I could not see any question in the chat box.
Sir, I would like to post a question. Mohammed Noor Faiz. Sir, can you please tell me if these masks are available or they'll be useful in the present pandemic, or you're working in that regard also? Or is it purely on defense that you are taking care of?
I didn't get the question. Can you repeat it for me?
These masks that you have made, they are mainly for the defense use. So are you also making something for civilians?
Yeah, because as I said before, there are two group of people that usually exposed to organophosphorus, which are military and also the agriculture sector. So this technology actually can benefit more for the agriculture sector because we use pesticide made from organophosphorus in a large amount every day. So it can benefit for agriculture sector, but more than military.
Yes, sir. Thank you.
Okay.
Welcome.
Dr. Noor, I would like to ask you one. I have basically one query. What is the particle size that can be filtered with the help of the nanocellulose filter?
Because in my study, I use cellulose nanofiber. So the fiber is interconnected with each other. So because since we use a cellulose nanofiber, is differ from the cellulose nanocrystal. So for cellulose nanofiber, it is difficult for us to measure the length of the fiber because it's interconnected.
No. I am asking something different. If we have air pollutants of different particle size,
I see.
what is the particle size that can be filtered effectively?
Okay, the pore size of the nanocellulose is below than 100 nanometer. So any of the pollutant has larger size than 100 nanometer can be filtered. Even the coronavirus also can be filtered by using nanocellulose. Currently, I'm also evaluate on the potential of nanocellulose to be used as the coronavirus filtration material. So we are currently investigating on it.
Okay, right. Thank you, Dr. Mohammad Noor, once again
Thank you,
for your nice presentation. Thank you.
Welcome. Thank you, Prof.
Okay, ma'am. Next presenters. Magdalena. Hello.
The presenter is present, sir.
Okay.
IP27.
Okay.
IP27.
IP27. Right. Okay. Now I would like to request Majliana Ahmed Kamaruddin from Malaysia to deliver talk on tuning the emission energy of colloidal quantum dots. Dr. Majliana, please.
All right. Hello, everyone.
Hello.
I request Dr. Mazliana Ahmed Kamruddin to enable her video if it is possible.
Sorry.
No
Yes.
problem.
Now it is available.
Okay. All right. So, Assalamualaikum and hello, everyone. Good morning, India. Good afternoon, Malaysia. And good day to everybody from all around the world. So, I'm Mazliana Ahmed Kamaruddin and I'm from Physics Department, University of Malaysia. So, today I would like to share with you about my work on the quantum dots, which is I'm doing a synthesis of the PBS quantum dots. This is in a colloidal form, but I also have an experience in growth the quantum dots using molecular beam epitaxy. But basically, in order for us to tune the energy, the concept is the same regardless the method that we use. So we know that currently quantum dots electronic properties are exploited for various applications, such as for bioimaging and optoelectronic. So like yesterday, we heard a few talks regarding the LED. So the quantum dots have also potential to be applied in biomedical. For example, if you loaded the drug inside the quantum dots, it can become as the drug delivery. So if you would like to apply for optoelectronic device, we can make a LED, which for example, currently we have quantum dot television where the view become more clearer. For example, the color of the blue becomes bluer, the color of the greens become greener, and so on. But the quantum dots application is not limited for optoelectronic and biomedical, but it also can be applied for the sensor and the storage. So this is an example of the application for the quantum dots. For PBS quantum dots, the emission is near infrared region. So here we can see that the comparison between the image when we use the quantum dot with different emission. So here is the application in bioimaging, and we can see that the quantum dot emit light in near infrared 1 windows and near infrared 2 windows. And we can see that by using near infrared 2 windows, the emission is become clearer, the images become sharper. So we can say that by using near infrared 2 windows, the quantum dot that emit light in near infrared 2 windows, for example, PBS quantum dots, it can reduce the photon scattering. It can have a deeper tissue penetration. It also can have a lower autofluorescence. And another example is I'm collaborate with the chemistry. They did the electrochemical sandwich immunosensor for detection of HER2 using antibody conjugated with the PBS quantum dot as a label. So you can refer to this paper for more details explanation. So I believe that majority of you are familiar with nanoparticles. So quantum dots is nanoparticles, but the physical dimension must be smaller than the exciton Bohr radius. So this is important because in order for us to get this strong confinement, the radius must be smaller than the exciton Bohr radius, which is the value of the exciton Bohr radius. It depends on the materials that you use. And quantum dots is crystalline and is categorized under zero-dimensional system. So this is the difference between the bulk and other dimensional system, which is the difference is in density of state. But I don't want to discuss more details about the density of state, but I would like to mention that in quantum dots, the density of state is discrete. That's why we can easily tune the energy bandgap. But it's probably hard for us to imagine how big is the quantum dots. So we can imagine we take the tennis ball and hair. So we can crush the tennis ball to 60 million small pieces. So one piece out of 60 millions is equivalent to the size of the quantum dots. Or quantum dots is very narrow. So for example, is 10,000 narrower than hair. So in order for us to express the energy of the quantum dots, normally people will use the Bruce equation. So the Bruce equation is used to express the confinement energy of the particles in box, especially in sphere or model. So we produce colloidal quantum dots and we assume that the quantum dots in our samples is in sphere. So the first term is referred to the energy bandgap in bulk, meaning that this value is constant and it depends on the materials. And the second terms is referred to the particles in bulk confinement, which is highly depends on the mass, effective mass of the electron and the effective mass of holes. And also it depends on the inverse radius square. All right. So, and the last term is referred to the Coulombic attraction between the electron and the holes. Because here we are talking about the exciton. The exciton means the electron and holes pair because they have a different charge. That's why they have a Coulomb attraction there. So in general, we can see here that the quantum dots energy is highly depends on the radius and the effective mass of the carrier of electron and holes. So from the equation, I would say that the energy of the quantum dots can be tuned with small changes of the value of the radius here. So as I mentioned, in my study, I synthesized PBS quantum dots. That's why here I draw all the PBS quantum dots and we try to tune the energy of the quantum dots. The first factors that the first approaches that we can use to adjust the emission is we can adjust the size. So we can grow a different size of the quantum dots. And then we also can dope the quantum dots with metal. For example, we can put a manganese. That's why we can have the excess of the carrier in the samples. We also can change, or we also can put a shell layer. So we can change the shell composition here. We can use a manganese sulfide, we can use manganese telluride and so on. So material of shell will change the confinement of the quantum dots. And finally, we also can change the thickness of the shells. So for example, if you already decide you would like to produce MNS core shell quantum dots, so you can change the thickness of the MNS shell layer in order for you to tune the quantum dots. So in summary, if you like to tune the quantum dot energy, we can change the size, we can dope the quantum dots, we can put a shell layer so it will form a core shell structure or core shell or whatever, or we can change the thickness of the shell. So whichever or whatever approach that we choose, what we did actually, we changed the confinement energy. So this phenomenon of raising excitant energy is reducing the crystallite size, which is known as the quantum confinement. So this is known as quantum confinement because as you can see that the animation here, so when I reduce the size of the box, the carrier is restricted in the small box. So I have an analogy. So if you can imagine you are sitting in the room and I reduce the height of the ceilings, you might need to bend your body because the height of the ceiling is getting reduced. And then after that, I will bring the wall left and right hand side close together. So you will sit in a very tiny room. In order for you to get free from this tiny room, you need high energy to release. So that is analogy what happened in the quantum dots. So same case happened in the core shell quantum dots. So at this point, the hydrogen wave-like function become squeezed. It depends, it's either type 1, type 2, reverse type 1 or reverse type 2 quantum dots. But the hydrogen wave function was squeezed due to the presence of the shell, so it will increase the energy of the electron holes pair. But today I will share with you my work on the PBS quantum dot, which is in PBS quantum dot we have is referred to the type 1 quantum dots. So this is the step how I synthesize a PBS quantum dot. First, we will prepare the core quantum dots, which is a PBS. And then we prepare the solution for the shell layer. And then after that, we will combine the solution of the core and shell in order for us to produce a core shell layer. And finally, we will do the characterization on the structural and the optical. So this is the details of the step how we synthesize the PBS quantum dots. So first we have to dissolve the lead acetate in the deionized water, and this become our lead precursor. And then we add a capping ligands, which is in my project I'm using a thiols, where I mix between the thioglycerol and dithioglycerol. And then after that, we adjust the pH by using triethylamine until we reach a pH 11. And then at the same time, we prepare the sulfur solution in a separate vials. And then after that, we're going to mix the lead precursor and sulfur precursor together. And it will form a dark brown solution, which is, it shows the formation of the PBS quantum dots. So here, when I mix PB, which is lead and sulfur solution, the precursor, I control the molar ratio to 1 to 0.3. So here, if you would like to synthesize core quantum dots, bare core quantum dots with different size, what you can do is you can change the molar ratio, because from my experience, when I increase the ratio of the sulfur, it will increase the size of the quantum dots. Then the next procedure is, once we prepare the PBS quantum dots, what we would like to do is we will mix it with the manganese precursor. So we just introduce the manganese precursor and mix with the PBS quantum dots, and we will form the core shell quantum dots. So what happened here is, in my PBS quantum dots, on the surface is sulfur rich. So when we introduce the manganese, what happened is there is a cation exchange between the manganese cation and the lead cation. So when manganese replace the position of the lead, then we will form the manganese sulfide shell layer. So this cation exchange is quite famous. So you just need to introduce one type of precursor in order for you to get the shell layer. So by increase the amount of the manganese solution, we can increase the thickness of the shell. So here is the HR10 images. It shows the different size of the quantum dots. The first image is referred to the PBS quantum dots, where the size is about 6 nanometer. And then when we add the manganese solution, we get the size of the quantum dots is increasing compared to the PBS quantum dots. So here we can see that the manganese shell layer was formed and the thickness was controlled by the amount of the manganese that we add in the PBS solution. So to confirm the formation of the MNS shell layer, what we did was we analyzed this image by using image J, and then we get the value of the plane and we compare with XRD data library. So from the value of the interplanar spacing, which is D spacing, we get the value of D spacing in PBS is referred to 0.34 nanometer. And this is corresponds to 1,1 plane, which is in the PBS cubic rock salt. And for PBS MNS, when we analyzed these samples, what we did was we measured the D spacing at the center of the quantum dots and also at the boundary of the quantum dots, and we get the value of D spacing is 0.3 and 0.26, and this is corresponds to 002 plane in cubic structure, which is referred to MNS and PBS core. And to even further confirm the presence of the manganese, what we did was we ran the EDX. So we found that the percentage between the lead and sulfur was 1 to 2, which is sulfur is more compared to the lead. This is expected because the amount of percentage of sulfur is double due to the presence of the sulfur in the ligands itself, the ligands that we use, which is thiols, and also the amount of the S sulfur that we add during the synthesis. And this is referred to EDX of the core shell sample 0.3, and we can see that there is a EDX peak at 5.9 keV, which is corresponds to the presence of the manganese. And then after that, we run PL. So this is the photoluminescence measured at room temperature. And this is for different shell thickness, where we grow the shell thickness from 0.3 until 1.5 monolayer. So we can see that when we run the PL, we can see there is a blue shift, meaning that it's confirmed the formation of the manganese shell, because the presence of the shell will increase the confinement of the carrier. So the blue shift confirm the MNS shell growth at different thickness, and this is due to the quantum confinement, which is here, as I mentioned before, that our quantum dot is a type 1, and the electron and holes is confined in PBS region. And when we grow the shell layer, we sandwich the PBS core. Okay, so when we sandwich the PBS core, so in order for us to create the exciton, it needs high energy. And we also do the calculation. My colleague did a calculation on the confinement charge carrier in the lead sulfide, zinc sulfide type 1 quantum dots by using the effective mass approximation. And she also found that when we increase the thickness of the shell, what happened is the confinement energy is also increased. So in theoretical and experimental, the result is the same. However, if you increase the thickness of the shell thicker and thicker, you might exceed the critical shell thickness, then you will get weak confinement. So it's not, I cannot promise that by having a shell layer, you can get a strong confinement, because it depends on your shell layer thickness. And after that, after we run the PL, we would like to see what happened to the samples when we anneal. So we do the photo enhancement. So photo enhancement means you anneal the samples under the laser, and we would like to see the increase in terms of the intensity. And here I just show you the sample of 0.3 monolayer, and by a nail the sample for 45 minutes, we can see that the intensity is keep increasing. So we tried for the other samples and we monitor in terms of the PL peak energy. So here when we increase the time, start from 0 until 40 minutes, we can see that for all samples, the PL peak energy is constant. However, for sample with the thicker shell, 1.5, we can see that there is oxidation, photooxidation. That's why we can see there is a shift in the photoluminescence. So to conclude my presentation, I would like to say that our synthesis in aqueous solution is successful, and we formed the core shell by using cation exchange reaction, and the samples, we can prevent the agglomeration up to 3 months. And from the PL, we can see that there is a strong confinement effect when we change the thickness of the shells. So I would like to acknowledge to UPM and Ministry of Higher Education for the grant, and I would like to thanks to my students for the hard work on the synthesis of the quantum dots. That's it. Thank you. I welcome for collaboration and any discussion.
Hello. Thank you, Dr. Majliana, for your nice presentation on lead sulfide based quantum dots. Can you hear?
Yes, yes, I can hear you.
Hello. Okay.
Yes, sir, we can hear you.
Okay. Now the session is open for question and answers.
There is a question from Dr. Rohit Sharma.
Okay. Dr. Rohit.
His question is, please comment on the lead-based quantum dots.
Yep. Oh, about the toxicity. All right. Okay. The lead base. All right. The lead base. Yes, everybody is afraid with lead because of toxicity. But we can. What we did in Nottingham University, because actually this work was done when I did my postdoc in UK. What they did was they cover with the liposome, with the protein, to control the toxicity, and also the how much you put the lead for the bioimaging. So there is a certain level it become toxic, but I didn't study on the toxicity. But in order for us to reduce the toxicity, we can use capping. For example, capping with the protein, capping with the silica. That is what I'm trying to do now, capping with the mesoporous nanosilica.
His another question was about the toxicity also.
Where is it?
What is your comment about the toxicity? And the second part you have already answered.
Yes.
Okay, can I ask one question, please?
Yes, sure.
Yes, yes, Dr.
Yeah, very nice presentation, doctor. Before that, good morning to everyone. This is Dr. Shankrama. So first question is, what is the motto of synthesis of core shell nanostructure? First question. Next question, you were claiming it is a core shell nanoparticle, but in HRTM, we couldn't find out it is a core shell formation. And one more thing I observed in the image, there is no crystal lattice form. So how can you say this is a core shell nanostructure? And how can you say about thickness of the shell? Can you please explain?
All right, thank you. The first question is, the second question about the formation of the core shell, how we confirm we produce the core shell. And the first question is?
What is the motto of synthesis of core shell nanostructure?
All right, okay. So here, why people grow the core shell quantum dots? Because if you grow the core only, the bare core without the shell, people try to tune the energy. All right. So for example, we managed to get the recipe to produce PBS quantum dot, but then the size that we get is only 6 nanometer. And we try to reduce the size further and further in order for us to tune the energy. then it didn't work because in order for us to synthesize even smaller, it's even harder. So what people can do is they can go for doping, they can go for core shell with the purpose to tune the energy. So that is the motto why people go to the core shell. But another motto is to trap the carrier inside the region. So for example, my work is in type 1. So in order for us to trap the carrier, we can put a shell layer so that it will sit inside the core region. So that's why people go for the core shell or core shell shell. So about the crystallinity, from here we can see that there is a diffraction pattern. There is a crystalline structure. There is a line there. So compared with the other area, it's just the amorphous. So by
Okay. Sorry to interrupt. So whatever the TEM image you are showing, I feel it is a might be a light lattice formation. I mean, crystal formation is happening. But the thing is, see, you observe in the top of the image. So most of the background is noises. So, and you are claiming that it is a core shell. So it should form a shell around the crystal structure. And how you can maintain? If you would have keep the sad image, it might be good impact of your claiming core shell. This is my suggestion. That's it.
Yeah, all right. Thank you for the suggestion. Because the lattice constant is quite similar, that's why when we do the image J analysis, we have to choose this area and the different area near the surface. If we do the analysis on here, it become error. You won't get any value. And then we compare with the XRD, because in order for us to run XRD on the quantum dots, we have to run SAX XRD, a small angle XRD is quite hard. So for the quantum dots, we have a problem, and so that we confirm with EDX and the photoluminescence to show that there is a confinement.
Then you are claiming shell size is this much, and all. But yeah, again, according to TEM images, it shouldn't be. Please, take a point to how you can claiming core shell and what basis you are going to analyze the cell thickness that under. I hope you know. And one more thing you told, the PL data based on that energy gap you find out. But I hope that is not sufficient. Already you claim it is a core shell. You can go for a DRS or be visible. So it will give a better band gap value about your core shell structure. And one more thing I want to add, not only the energy or not only the reducing the size you are going to synthesis core shell nanoparticle. In order to that, you can add three more points based on the property. We can tune all the properties when you go for a core shell nanoparticle, as well as based on the application we can do, right? Yes. Little bit work has been done regarding core shell. That's what I'm telling. That's it.
All right. Okay.
Nice presentation.
Yeah. Thank you.
Thank you, Dr. Sankaramma, for making nice queries and basically suggesting the young people.
Thank you, sir.
Thank you.
Thank you, sir.
Dr. Majliana, for your nice presentation and answering the questions and queries nicely. Now, we have the next presenter, Wu Ha Juin, again from Malaysia. Can I see Wu Ha Juin? Hello?
Yes, he is in the present. Is this?
Is he there?
He is there, sir, in the participants. Allow him some time, sir.
Okay.
Can you hear me?
Yes, we can hear you.
Yes.
Okay. I'm sharing my screen. Wait a minute.
So, Yes, now it is visible. Maximize it, please. So, Dr. Wu is going to present on Prussian blue as cathode material for sodium-ion batteries with high electrochemical performance.
Thank
Dr.
you.
Wu?
Yes,
please.
thank you, Chairperson. Good morning. First of all, I'd like to thank the organizer and the invitation from Professor P.K. Singh for giving me this opportunity to present my work here. My presentation today is Prussian blue as cathode materials for sodium-ion batteries with high electrochemical performance. First of all, I'd like to thank my student Chen Yun Chai because he's the one who did this experimental work. And he also prepared part of the slides today. I'm from Malaysia, so greetings from Malaysia, University Malaya, and I attached to Physics Department, Research Center for Ionics, University of Malaya. This is my presentation outline. I'll start with an introduction. Why sodium-ion batteries? The main challenges for sodium-ion batteries, Prussian blue and its analog. And after that, I'll continue with some results and discussion on our first attempt of preparing, synthesizing Prussian blue, and then the sodium-rich Prussian blue and acid etching Prussian blue. And I will end with conclusion and acknowledgement. Well, many decades ago, people started to talk about energy crisis, right? Where we have this depleting issue of the natural gas and oil. And after that, people come up with this solution using the renewable energies, also coupled with the development of the electric vehicle. So we have all these renewable energy power plant, and that we integrated into the smart grid electrical systems to power homes. However, renewable energy such as solar energy, wind power, or hydroelectric, they do not produce electricity all day long or at all seasons. Therefore, we need these rechargeable energy storage systems to support. So the main keyword here is rechargeable and also this stationary, because we are not using these energy storage systems as a mobile devices, but we put it in just next to the power plant. So why sodium-ion battery? Well, if you look at this chart for lithium contract price, the price basically increases drastically over the 2 decades. And if you look at our Earth crust, sodium reserve has 2.36%. If you compare to lithium, which is 0.0065%, it has more than 300 times of the reserve. And because of the abundance of sodium, the cost is very low. Now, if we compare to lithium, lithium being the lightest metal in the world, in the periodic table, no other material can actually compare to lithium in terms of the weight. Therefore, lithium-ion batteries has the maximum or the highest gravimetric energy density, right? Or we call it a specific energy. But if you use this energy storage device to support the power plant, where the weight may not be the essential factor, then what we are saying here is sodium-ion battery could be suitable for large or medium scale stationary energy storage systems. So we will emphasize the word stationary here. Being on the same group as lithium, sodium on the periodic table, sodium-ion battery basically has similar working mechanism like a lithium battery in terms of charging and discharging, just as shown here. Due to time constraint, I'll go fast for this. there are some main challenges for sodium-ion battery. First of all, the low specific capacity compared to lithium-ion battery, 1.16 ampere-hour per gram compared to 3.86 ampere-hour per gram. And the heavy mass of the sodium, which is 23 versus lithium 7, and the bulky size with a large ionic radius of sodium ion being 98 pm picometer versus 69 picometer for lithium, it makes it very hard to move in between the two electrodes, cathode and anode. And this also caused a short cycling life of the sodium-ion batteries. There are some candidates being investigated for cathode material for sodium-ion batteries, such as the transition metal oxides, polyanionic compounds, organic compounds, hexacyanometallites, and others. And my work here today will talk about this hexacyanometallites material, Prussian blue. And hexacyanometallites has a specific specific capacity shown here with the operating potential as given here, light purple color. What is a Prussian blue? Prussian blue basically is a dye material, like what is shown here, the blue color dye, with a given chemical formula, such as shown here. And Prussian blue analog has a chemical formula being shown here. A represents the alkali metal, Fe, FeCN6, and this empty box represents the vacancy or the defects of the crystal structure. And this H2O is the interstitial water. Now, based on literature review, different group of researchers are trying to synthesize a less defect crystal of Prussian blue analog with this empty box value 1 minus y as low as possible, because their observation is that whenever there is a high vacancy or a high defect, the interstitial water will basically fill up the vacancy, and that blocks the insertion and desertion of the sodium-ion battery. Okay, now this is the two-dimension diagram of a Prussian blue analog, with a black dot here represent the carbon atom, and blue dot here represent the nitrogen atom. Now, what happened during the charge and discharging process? The sodium insertion and extraction basically come through this channel, okay? C and N will open up, and then sodium will come in and then go up accordingly. This is a 3D image. Now, the main important for the synthesis of the cathode material is that if you want something that is very rigid, a framework that allows the last channel, okay, for sodium ion insertion and extraction. And this framework must be very strong and rigid and can last for long cycles. So this is what people aim to produce. This is our work. We prepare this material using single ion source slow precipitation method. In our first attempt of preparing Prussian blue, this is a methodology. Basically, we add in all the starting reagents, mix and stir for 30 minutes at 60 degrees Celsius, and we'll be obtaining a yellow solution here, okay? Then we keep it into electric oven, heat it again for 24 hours at 80 degrees Celsius. We'll be obtaining a blue suspension. Then we'll continue to age it for another 2 days, 48 hours. Then we collect it using a high-speed centrifugation, and then we wash it. After that, we vacuum dry it, okay, for 1 day. With the obtained Prussian blue powder, we send the product as prepared product for TGV. This is what we obtain. if you look at it, in between 50 to 250 degrees C, there is a drop of about 5%. Basically, this wet loss is due to the water content inside the material. And above 450 degrees, we observe a PB collapse. They start to collapse and decompose. Then we also send for XRD. This is XRD spectra. Well, basically all the peaks are sharp and strong, and they're in agreement with the library data from JCPDS number 521907, with all the important peaks being agreed, okay? And having this space group of FM bar 3M, a cubic structure. Then we also look at the FISEM images. Basically, we have a distribution of different sizes of cubic in between 400 to 800 nanometer. And we also run the XPS result to look at the valence of the ion. So we have iron 2+ and iron 3+, and from the area under the curve, we found out the ratio is to be 0.93. We also did the EDX to look at the elemental analysis. And this is what we obtained. From this EDX, we obtained the element weight ratio. And also we run the CHN elemental analysis to look at the amount of C, H, and N. And combining with XPS result, this is what we obtained. As tabulated in table 1, the element ratio composition of our product. With this, we use the atomic weight, divide it and normalize it to Fe3+ to obtain the PB analog formula as given here. So we have a sodium 0.58, Fe3+, Fe2+, CN6, 0.93, and with a vacancy value of 0.07 and an interstitial water of 1.70. This is considered a quite good result because we're quite low vacancy amount here, 0.07, and we were excited to test for the electrochemical performance of a sodium-ion battery. So this is how we fabricate the coin cell to run the electrochemical test. So first of all, the active material as prepared Prussian blue was added with PVDF as a binder and activated carbon 811 or 801010, and then the slurry we put it on the thin aluminum foil, and then we dry it. So then we stem cut it into a circular shape. That is our cathode material. And then we sandwich this cathode material, sandwiching with the electrolyte material, sodium NaPF6 in ECPC and FEC 11 and 5%. Another type of electrolyte that we tested is NaClO4 in EC and DMC ratio 1:1. This is a half cell testing. So we use anode, the sodium foil as the anode material. And we send for testing, running for the cyclic watermetry, rate performance, and charge discharge. This is the CV result. Now, there are basically two pairs of redox, okay, that representing first of all, the 3.15 watt and 2.74 watt pair. This represents the high spin of Fe2+ at 3+. And then the second pair at 3.78 watt and 3.63 watt, that represent the low spin of Fe2+ to Fe3+. And then we also run the GCD. This is what we obtain at 0.1 C rating. We are getting 123 milliampere hour per gram. This result is considered quite good result. However, this is at low C rate, okay? Then we also tested for higher C rating. slowly increase to 0.2 C and to 0.3 C. It works with quite high efficiency, Coulombic efficiency, close to 100, or above 100 milliampere hour per gram. Then we run for 1 C, and we obtain after 200 cycles, it retained 90% of the capacity. We couldn't run higher C rate higher than 1 C because the product is no longer stable, okay, at higher C rating. So this is the schematic diagram of our synthesis Prussian blue. Then we move on to try another way. We are still using the same methodology, but now we try to produce what we call the sodium-rich Prussian blue by adding an element here in this step 2. So step 2, instead of just adding the hydrochloric acid, now we add in this sodium chloride, okay? We add in additional starting reagent, sodium chloride, with 0 mole, 1 mole, 2 molar, and 4 molar. And the rest of the steps are the same. This is what we obtain for TGV. Well, if we compare to the earlier Prussian blue, again, we have around less than 5% of the water content. Then after that, we observe that for Prussian blue, 2M and 4M, it shows higher thermal stability. Then we also try to run the EDX mapping, and we found that for sodium, iron, and nitrogen elements, their distribution are quite uniform. This is the XRD result. This is an interesting result because for Prussian blue PB0M, we obtain a cubic as we increase more and more sodium content, okay, inside the Prussian blue. What we observe is we are still getting all the peak, but with a slight shift to the left, okay? And as we run the matching, we found that instead of cubic structure, now it turned to rhombohedra, okay? So the lattice system has changed slowly from cubic and rhombohedra. As you know, cubic has a lattice parameter with the length, parameter A length equal to B and C. Likewise for rhombohedra, but cubic, the lattice axial angle are making right angle with one another, right? 90 degree, A to B, B to C, and C to A. However, rhombohedra, they do not make 90 degree. So what happened here when we produce this so-called Prussian blue, sodium-rich Prussian blue? From calculation, we find that the lattice parameter are increasing from 10.22 to 10.225, 10.23, and eventually 10.24, respectively. Then we try to search about it, and we found that this result is in agreement and with similar observation with another group of researchers reported in the literature, whereas they run the in situ XRD result during charge and discharging. The insertion of sodium ion into the Prussian blue, like this, eventually will create a little bit of distortion where the angle, the axial angle, no longer making a right angle or 90 degree. Therefore, the cubic will change or move to rhombohedra. So in our case, we are not running charge and discharging here. We are preparing a sodium-rich Prussian blue. And yet we obtain the similar result in terms of XRD. So we concluded that it is very possible that the sodium-rich Prussian blue here, the additional sodium are actually embedded inside the crystal, the unit cell here, and that may cause a little distortion to the cubic lattice system. Then what about SEM images? Well, this is what we obtain, a cubic. As we add in more and more sodium rich, we obtain a very rough surface for PB1M. rod-like surface for PP2M and very porous for PP4M. Very porous cubic here. Then, of course, the next analysis that we want to run is to check the surface area. So we are running the nitrogen gas absorption desorption analysis, and you find that the surface area increases from 2.07 to 2.64 and eventually 28.38 meters square per gram, respectively, for PP1M, 2M, and 4M. So this is the EDX, CHN analysis, and XPS result. We also do the same for this and tabulate this table. And the amount of sodium here increasing, okay, from PP0M to PP4M. And this is a schematic diagram of the sodium-rich Prussian blue synthesis. Next, we are very eager to run to test for the electrochemical performance. Now, remember earlier, I mentioned we couldn't run more than 1 C rating. What happened when we do that? Now, C rating, for 1 C rating, this is the blue color, getting about 90 plus. As we increase the C rating to 5C, the performance, it performed poorly, about half of the value, okay? Now, as we are preparing the PP from 0M to 1M, 2M, and 4M, we observe that the performance at high C rating is getting better and better. Let's look at this PP4M. Now, the 5C rating, which is a green line, is quite good actually, right? Compared to others lower C rating. Not much different, maybe 10 to 20% of drop instead of 50%. So we are very happy about this. Then we recall back in our TGA analysis, it has a higher thermal stability, right? Therefore, we also run the thermal, battery at elevated temperature. But before that, what is this C rating? Now, for 1 C rating, it means it takes 1 hour to charge fully, okay? To charge or discharge fully, 1 C rating. What we usually buy, the battery, there are some rating given there, right? From the manufacturer. So what they did usually, in order to show a very nice reading, right? They usually run and test their battery at 0.05 C, which takes about 20 hours of charging in order to get a nice reading. For example, a 150 milliampere hour per gram, okay? But if you run for 1 C, like what we obtain here, we will be getting a very low specific capacity value. So what manufacturers show us is actually at the 0.05 C. Now, if we run higher than 1 C, it actually takes shorter time to charge. For example, 5 C, it takes only 12 minutes to charge your battery. So obviously, we want a battery that can run higher C rating, right? This is what we want, what we aim for. Okay, let's look at elevated temperature battery performance. Now, for PP0M, we couldn't run a long cycles for battery even at 60 degrees C. Look at here. The performance dropped drastically. This is 5C rating. It dropped drastically, and at 80 degrees C, no, it will not perform at all. As we improve the Prussian blue, the sodium content from PP1M to 2M and 4M, we find that at elevated temperature, sodium-rich Prussian blue can actually perform as a sodium-ion battery better, much better than the PP0M. Okay. Now look at this, the 5C rating. We can run, it still shows us a quite good performance, close to 100 milliampere hour per gram. What about for long cycles? Well, this is the result for PP4M. We run it at 2C rating at 80 degree. this one, this line, it shows still more than 60 milliampere hour per gram after 500 cycles. Okay, next. So next we now we try to repeat the same methodology, but now we try to use acid to etch it. So what we call here acid etching and double heating process. Now at this step 6 here, instead of vacuum drying, now we add in acid, hydrochloric acid, 1 molar to etch it, okay? And we call it PPA. And at the same time, this step 3, instead of just vacuum heat it at 80 degrees for 1 day and cool it down, now we repeat the heating process. We call it double heating because after you cool down to room temperature for 1 day, 1 day later, we heat up again at 80 degrees and cool it down for 24 hours again. So double heating, and we call it PBC, okay? So PPA represent acid etching, PPC represent acid etching with double heating process. Well, this is what we obtain for PPA. This is what we obtain PPC here, and we find that for PPC, the double heating, we obtain more and more similar size of the cubic structure Prussian blue. And after etching, this is what we found. The surface are etched with porous surface. This is PPC. Then of course we test the, we want to calculate the specific surface area. Now this is the XRD diagram. Not much changes. All the sharp peaks are still there. This is TGV result. This is a specific surface area for PPA. Now, after etching, we are getting 6.6 meters square per gram. After etching with double heating, we are getting 79.3. And with very narrow pore size distribution here, in between 5 to 10 nanometer. Therefore, of course, we can't wait to test for the electrochemical performance. This is the result for PPA and PPC. Now we run at higher C rating, up to 10 C, okay? It still works, although the performance drops. And for PPC, the performance dropped a little for C rating as high as 10 C, okay? And this is the cycling result. For, if you look at here, for 10 C rating, we obtain 97 milliampere hour per gram after 35 cycles. And much improved result compared to our 2 previous systems. And this is for long cycles, over 1,000 cycles retention. We retained 85% of the capacity at 1 C rate, okay? And this is a schematic diagram of the Prussian blue acid etching and double heating. This is a conclusion. Prussian blue cathode materials for sodium-ion batteries are successfully synthesized via this simple ion source slow precipitation method. And its morphology, structure stability, and thermal stability can be controlled to achieve good electrochemical performance at high C rating and also elevated operating temperature. I also would like to thank the Ministry of Higher Education Malaysia for the financial support, and also University of Malaya. And also would like to thank the support from Research Center for Ionics, University of Malaya. And also I would like to thank our collaborator, Professor Fei Wang from the Southern University of Science and Technology, China. This is the references, and thank you for your attention.
Okay, thank you, Dr. Wu, for your detailed presentation on Prussian blue-based cathode materials for sodium-ion batteries. And now the session is open for questions and queries. Is there any question? Okay. Dr. Wu, you have said that the product is unstable after 1C rating of charge discharge.
Yeah.
I would like to know which kind of degradation is taking place in your material.
Thank you for the question, Dr. Sukla. Yeah, basically, for those who are running the battery cycling process, after long cycles, we find that the insertion and desertion of the sodium ion inside the electrode material no longer as efficient as the first cycle. Okay, there are a few reasons for that. First of all, it could be due to the formation of the solid electrolyte interface material in between the electrolyte and the cathode. So whenever in every cycle, whenever the insertion or desertion of the sodium occur, yeah, there is a high chance it will form a thin layer of this SCI, and that causes the degradation of the cycling performance. This is one factor. Second factor is the unit cell, the crystal structure, the framework. Now, when every time insertion, basically the framework get expand, right? With the additional of sodium ion come in, and then extract, then it contract. So all the expansion and contraction, the efficiency drops with these the efficiency drops with increasing of the cycles. Yeah, that causes the poor performance of the sodium ion battery.
Okay. So expansion and suppression of electrode electrolyte interface is taking place, or something else, where compression and expansion is taking place.
Yeah, there are two. There are more than one factor involved, causing the cycling performance to drop. Yeah.
No, I am asking.
Yeah.
At whether it is taking place at the cathode or anode or in electrolyte material.
Sorry, what is your question? You're asking what is taking place?
I'm asking compression.
Yeah.
While the charging and discharging takes place, you said compression and rarefaction is taking place at some point.
It occurs at the electrode side, because the extraction or insertion of sodium ions. So insertion of sodium ions, you have sodium ion coming into the electrode, into the cathode, and then going out extractions. So during charge and discharging, this occur. Yeah.
At cathode side.
Yes.
Okay. Thank you. Thank you, Dr. Wu.
Thank you for your question.
Nicely presenting the talk, and you have presented in much greater detail about the sodium ion batteries and how the pressure group can be used as a good material for getting a good performance battery. Thank you once again, Dr. Wu. Okay, so now we have another invited presentation on inorganic nanotube and fullerene like nanoparticles, the crossroad between material science and technology and their applications. The presentation I would like to invite Dr. Artene from Israel.
Good morning, everybody. I have to share the screen, I guess.
Okay, please.
Yeah, okay, I'm sharing my screen, and I'll show you the
yes, it is visual.
Do you see me?
Yes, it is visual.
Okay, good morning, everybody. I'm Reshev Tene from the Weizmann Institute in Rehovot, near Tel Aviv, in Israel. And what I would like to present to you today is some studies that we have carried out over the last 30 years on 2D materials. And in particular, the use as bed for synthesis of new nanostructures, inorganic nanotubes and Fullerene-like nanoparticles. This study came immediately after the study of the report of Ijima on carbon nanotubes. And I will give you some background before going to some details. Of course, it's not possible to review extensive work that has been done of this scale in 30 minutes, but I'll give you a glimpse of what we have found and what others have found. And I hope that you are enriching yourself with an information that you may not be exposed in general. So the study was carried out mostly in the Weizmann Institute, but of course there are many groups all over the world involved in that. And I will present you some work. So let me start first by telling you a little bit about 2D materials. We all are excited now about 2D materials, but in fact, 2D materials research started 100 years ago. And one of the early works that have been done systematically was by Linus Pauling during his PhD thesis in Caltech, where he showed, or where he studied with X-ray diffraction, the structure of molybdenum disulfide. And molybdenum disulfide is molybdenite is a mineral available in nature. And he could show that he can cleave it with a scotch tape or with similar technique, maybe with a razor, and get fresh surfaces to study their X-ray diffraction. And this is not, this is the first time that at least I know of in the literature that cleaving of layered materials is reported. So he studied these materials first, and he found that they are very strange, that they have the C-axis is 7 angstrom, or is 6 angstrom as separation between the layers. This means that there is no chemical bond holding the layers together. So he concluded that these materials are very anisotropic, have very anisotropic properties, and the chemical bonding in the layers in the AB plane is covalent, of course, between the tungsten and, let me just present with laser viewer. Where is the pointer? So basically the layers are of molybdenum is sandwiched between 12 sulfur layers, and it's covalently bonded between the molybdenum and sulfur, yet between the layers there is a van der Waals interaction only, which is 50 times weaker than the covalent bonds or even more. Then in 1930, and I'm skipping many studies, but in 1930, Linus Pauling, he was already a young researcher. He started to study other layered compounds, and in particular, the natural occurring alumosilicate and germanosilicate. And they are made of a special layer, and he divided them into 2 groups. The groups of this is an infinite layer of silica connected to alumina via oxygen atoms in between the 2 layers. And as you see, this layer is not symmetric. The basis in the alumina is smaller than the basis in the silica. And consequently, in the first paragraph of the paper, he predicted that this nanotube, these structures will not be stable as planar structures and will form tubular structure in our concept, which did not exist, of course, at that time. There was no electron microscopy to verify nanotubes, but yet he predicted via his X-ray studies that these materials are not stable in the planar form and will form folded structures. And it took another 20 years to find these nanotubes in 1950s, when electron microscopy was of high resolution already to observe such nanotubes. These first nanotubes were reported. So we are not, in that respect, nanotubes is a not new animal in chemistry. It's an old animal, and we have to understand that there are different kinds of nanotubes from different layered materials and non-layered materials as well. But if you talk about 2D materials, certainly Linus Pauling is the first proponent of this idea of nanotubes from alumosilicate, germanium silicate, which are available in nature. And he also said in the same paragraph that molybdenum disulfide, which is a symmetric material like mica. Mica has two silica and one alumina, so it's a symmetric structure on both edges. It won't fold. And he said that molybdenum disulfide will not fold and won't form nanotubes. In that respect, he was wrong. And let me go directly into the third graph or slide, which shows why these materials are forming nanotubes. So as we all know, in 1985, Kroto and Smalley and Kerr discovered the C60, and the C60 is made of 60 atoms of carbon with 12 pentagons and 20 hexagon, and they form a closed structure. Now, why do they form this closed structure? If you look on carbon, on graphite, you see that most of the atoms are three-fold bonded. Each carbon atom is bonded to 3 carbon atoms. But on the rim, they are only 2-fold bonded. And if you make graphite small enough so that there will be more atoms on the rim compared to the bulk, they will spontaneously fold. It pays them to fold and thin and close into structure as C60. And this was 1985, and as you well know, the Nobel Prize went to them in 1996 or 1995, I don't recall. And then in 1991, Ijima proposed, actually it was already in the literature, but Ijima proposed very, very nicely, observed that these structures also form the carbon nanostructure or graphite nanostructures are not stable, and they can form nanotubes. And from that, the whole science of carbon nanotubes started from that point in 1991. Viewing these beautiful works, I decided to explore the possibilities that molybdenum disulfide and tungsten disulfide will also form nanotubes. The reason being that they are also, like graphite, they are layered compounds. Here you have molybdenum or tungsten sandwiched between 2 layers of sulfur. So it's more difficult for them to bend and form nanotubes. But nevertheless, if you look on molybdenum disulfide from the C-axis, here you have one sheet of molybdenum disulfide. You see that the molybdenum in the edge is only 4-fold bonded, and so 2 dangling bonds are missing. And the same is for the sulfur. The sulfur is only 2-fold bonded instead of being 3-fold bonded in the bulk. Therefore, I hypothesized that these structures will form nanotubes and fullerenes, which was realized by looking in electron microscopy of thin films of molybdenum disulfide and tungsten disulfide. And the first credit should go to the late Dr. Lev Margulis, who found this in, you can see here the dates, 8th of August 91. We already saw in these envelopes of slides of TEM, we already see it's written in Hebrew, but nevertheless, or red blood cells, he called them because they are hollow and they are like donuts, hollow donuts. So let me show you these structures. So that's what we saw. He and I saw these beautiful closed structures of tungsten disulfide, which are made of layers of tungsten disulfide folded and close together, one layer after the other. So they are not perfect like C60, but nevertheless, you have, and there are many, many atoms here, probably 1 million atoms of molybdenum and sulfur, or tungsten and sulfur. And so here is for tungsten disulfide, here is for molybdenum disulfide. and we call them IF molybdenum disulfide or IF tungsten disulfide because they are Fullerene-like structures. And indeed, it took us a long time to be able to come up and synthesize them in large amount. In the first thing, we saw them in very small amount, but slowly we developed the chemistry that allowed us to get this metastable phase. It's always a metastable phase, and I cannot go to the details, but theory will tell you that this is a metastable phase, but it's very, very stable at room temperature, and they form these hollow closed structures. And you see that we get pure materials now, and in fact, we went to industrial production. There is a company or few companies that went to industrial production, and you can buy them in the market now. So what are they good for? I will skip a lot of research, but I will go immediately to lubrication. If you want to have a good lubricant, you must have a material that can go into the space between the two surfaces and exhibit very, very low shear forces between the two surfaces. And if you go to the history, we know that the Egyptians already used lubricants. Here you see this person pouring oil or water in front of this huge statue, which thousands slaves attract. So they actually is the work of these slaves to attract to track these statues over hundreds of kilometers in old Egypt. And the same is they use also, instead of oil, they use the logs, tree logs, and you can see these two gentlemen putting these tree logs, which are beneath this ship. And so for the Maya culture, also they use the same concept of 1,000 years ago. They use these logs to lubricate. But nowadays, of course, we are able to do that on the nanoscale. And what they did is on a macro scale or on the very large scale, and we are doing that on a nanoscale. And here is an example, very, very small example out of many, many studies, which shows you this Fullerene-like nanoparticles getting in between the surfaces of metal and actually lubricating together with oil. They are added as a 1% or less into the oil, and they lubricate under high loads. They lubricate very well the surfaces. And this graph shows the behavior of oil by itself as a function, the friction. And you see that after some time, the friction goes to 0.1. But when you use these Fullerene-like nanoparticles, the friction is cut by half. And if you go use platelets of molybdenum disulfide, it is also very small in the beginning, initially, but eventually the friction goes up because the molybdenum disulfide platelets are burned. So this is just a glimpse of huge studies that we and others have studied, and this is now technologically available. There are quite a number of companies that are using these lubricants, which started in my laboratory. And the mechanism, we have studied the mechanism of lubrication, which is quite different from the known lubrication mechanism. So in the case of molybdenum disulfide, it is well known that it lubricates by shearing the layers on top of each other. But here, because you have a closed structure, they cannot shear. Instead, they roll, and rolling friction is a technique which gives or a mechanism that provides very, very low friction coefficient. And you can go to even under heavy loads of 0.6 gigapascal and 1 gigapascal, which accounts to actually 10 tons of load on your fingernail. You get a very, very low friction coefficient. So this has been beautifully shown by in situ microscopy, which I'll not discuss later further, by Ofer Devet from my group and Fabrice Desanoy from Lyon. And this is demonstrating the usefulness of these nanoparticles as lubricant. Let me go directly now. I'll save a lot of time. I'll go now to the nanotubes, which we reported also in the same in the same paper. And we showed in the first early papers in Nature, and we showed that we can make nanotubes. Look on them now, we can make them in kilograms in a pure form, tungsten disulfide nanotubes, molybdenum disulfide nanotubes. This is done in my group and in other groups, mostly by Dr. Alazak from the Holon Institute of Technology, a former student of mine. She's a professor in Holon Institute of Technology, which is not far from here. So here's a recent paper of her group. For years, we struggled with the molybdenum disulfide nanotubes, and we could sporadically synthesize them, but not in a systematic way. So as I mentioned to you, we always start from tungsten oxide, or if we want to make them in large quantities, we start from tungsten oxide. She started from molybdenum oxide, and by heating gradually the molybdenum oxide and using larger and larger fluxes of hydrogen sulfide and hydrogen, she could make eventually macroscopic amounts of molybdenum disulfide nanotubes. And this provides a very good material for lots of studies, and we are undertaking now serious together jointly or herself. We do a lot of studies on the fundamental properties of this nanotube. Let me show you some few applications or few potential applications or applications of nanotubes of this kind. So they are obviously weaker than carbon nanotubes, but in contrast to carbon nanotubes, they have a big advantage in three different areas. First of all, they are not toxic. This is very important because carbon nanotubes in the EU now is banned from many products due to the toxicity. So here there is no issue of toxicity so far as we know. And there is, of course, a room for many, many more studies on this. But so far, we know that these are non-toxic. The other advantage of tungsten disulfide nanotubes is that they do not agglomerate very strongly because they don't have the pi-pi staking like carbon nanotubes or like graphene. Graphene has a lot of pi forces due to the aromaticity of the layers. They stake very much and they agglomerate, and it's difficult to separate them. And if you separate them, you have to invest energy, and then you ruin your material, or you find a smart way to separate them by surfactant. And then the question if the surfactant is not affecting the interface with the other matrix. So here we take tungsten disulfide nanotubes, simply spreading them in the PLLA in this case, which is very important for medical applications. There are many, many medical applications based on PLLA. And then we measure the stress strain curve, which is the typical classification of mechanical properties. So the stress of the PLLA itself is like this. It's very weak, relatively weak. And if you add the nanotubes, it becomes as strong as 60 megapascal, and the elongation can go as much as 15%. And the work that the fracture toughness of these materials is enormously larger compared to the original material. So instead of having toughness in this case is as in the pure PLLA is 1.2, and here it's almost 4, which is a factor of 3 or 3.5 larger. So this gives a very big advantage for many medical products. And indeed, now we have several collaborations with medical companies to try to develop products based on these materials. So here is a 3D printing of an air. This is a work with Dr. Noah Lachman, which was published recently in a scientific report. But there are many other groups, like the group of Nafach and Ilis, and that published a lot of works on polymers impregnated with these nanotubes. And I won't go further because, maybe I'll show you one more example. This is the example of shooting a projectile into a sheet, which is sheeted and having some nanotubes in, and very shortly, very briefly, you see the system, and you see that when you shoot the bullet into the nude sheet, the bullet penetrates. This is the vision from beneath the sheet, while if you put the nanotubes in, the bullet simply does not penetrate the sheet and protects the people behind it. So that is of course, a very important defense potential for these materials, and several groups are working now on the applications of this product to the market. I won't go to the details, but just to show you, demonstrate you two pictures of how flexible and strong are these nanotubes, which gives them a very strong edge for very high variety of applications. And I remind you that they are non-toxic, and there are some other advantages that I won't deliberate on, but they are of course weaker than carbon nanotubes. Let me go directly into very briefly into some very recent studies on 1D superconductivity. This was done with Yoshi Iwasa in Nature Communication, published in Nature Communication quite recently, and in Nano Letters. And what we see here, he takes one nanotube and measure the conductivity as a function of temperature, and see a 1D superconductivity, clear 1D superconductivity. And the way that you can judge that this is 1D superconductivity, I won't go to the details, but this is a little Hertz oscillation. The Cooper pairs simply interfere with each other and form an interference pattern, and therefore they can circulate in phase in the nanotube, and they form these oscillations which come very close to the critical temperature, but not above that. So this is one demonstration of the 1D nature. The other nature, there are several papers now that we have published, and others on the properties. As you know, 2D materials, thick 2D materials do not luminesce, but they scatter a lot of light, and we can see this light scattering by forming a polariton. And this is a study that was started by my former student Lena Yadgarov, and you see the polariton. If you compare the absorption spectrum of these nanotubes in solution to the extinction spectrum, you see that there is a big shift in the spectrum compared to the A and B excitons, and this shift was explicitly explained via polariton. Polariton is a hybridization of a cavity mode that goes in the nanotubes like a fiber, enclave the optical mode into the nanotube, and then interact with the excitons and hybridize with the exciton, forms strong coupling and polariton. And I won't go to the details because I don't have time. Let me go to the last part of my talk, and this will be on misfit compounds, 2D misfit compound. These are extremely interesting and nice materials. Again, layered compounds which are made of pairs of hexagonal materials like tantalum disulfide or niobium disulfide, and rock salt structures like PBS or lanthanum sulfide. And these structures are typical 2D materials but they come in pairs. There is a charge transfer usually from the rock salt to the hexagonal sheet, and this charge transfer stabilize the 2D structure, this a pair of 2D materials that form together. And I won't go to the details, but just say that these are called misfit structures because there is a misfit. Along the A-axis, the rock salt and the tantalum disulfide or niobium disulfide do not disagree, and they are incommensurate. And consequently, you don't have a real unit cell in these structures. But nevertheless, they form layered compounds, platelets. And what we have done is that we have actually used the concept of Pauling which stated that in such situation, the layer will naturally fold, and indeed it folds. And if you give it you use a smart chemistry, you can close it from a folded structure into a nanotubes. And that allowed us in a very short time, using chemical vapor transport, to get many, many nanotubes from misfit layered compound. And there are hundreds, if not more. And now we make them from alloys, quaternary, and the number is unlimited because you have alloys in different composition. But let me just show you very shortly the nanotubes. And here you can get an impression. This is a nanotube from I believe from lanthanum sulfide, tantalum disulfide, or in this case, it's a samarium sulfide, the rock salt samarium sulfide, one layer of samarium sulfide goes in between. In this case, it's 2 layers of samarium sulfide go in. Sorry, there is a 1 layer of samarium sulfide, 1 layer of tantalum disulfide, 1 layer of rock salt samarium sulfide, 1 layer of tantalum disulfide. And you see them very nicely. You can superimpose the calculated structure on the nanotube. This is the nanotube. You can see that this is nanotube. And we can make sections. We can actually cut these nanotubes now very nicely with FIB, and we can see the sections. And if we go to the sections, actually, this is a high resolution image of a section that was built. It's like a coin from the nanotubes. So you see that it's a multi-layers structure, and you see the section, and you see beautifully the atoms of the samarium and the sulfur. Here you don't see clearly the tantalum, but the black line is basically tantalum. And if you go to a close-up of the structure, now it's not a cross-section. This is an yttrium. It's an example of another study on yttrium sulfide, tantalum disulfide. Here you can already see all the layers, all the atoms. So you see the yttrium atom is here, the sulfur atom is aside, and here is the tantalum disulfide. You see the sulfur atoms, and this is very important information on the structure of these materials and the nanotubes. And we can understand from this, we can calculate the properties of these nanotubes, and we find that they are semi-metallic and they have some other interesting properties. And we study them now in greater detail. I think I'll show you now, I think this is the last slide that I want to show you. This is a cross-section of a new nanotubes, which we have synthesized and is in PNAS in revision. So this is a quaternary nanotube, but very interestingly, here we mix sulfur and selenium, and the sulfur combines with the lanthanum, but not with the tantalum. And if you go to very small amounts of sulfur, basically the material is starved of sulfur. It forms multi-layers of tantalum diselenide because the selenium binds to tantalum only and the lanthanum binds to sulfur only. And we get, because there is not enough sulfur, we get multi-layers of tantalum selenide per 1 layer of lanthanum sulfide. And that is seen beautifully here. You see the structure, you can see each and every atom in this structure. You can analyze it chemically by EDS, high resolution EDS, and you can see, you can understand the chemistry via the high resolution TEM and related studies. So I won't go into the details, but we do a lot of EXAF studies and ZANES and other studies to check these materials, and we understand them in quite detail now. We don't have any applications to these materials as yet, but they are only 10 years old, and hopefully sometime in the future. Actually, we have proposed recently some electronic device, which I cannot stipulate here. And I'm sure that there will be some application in the future, but I'm not worried at this point. I'm interested in the chemistry. And so I scanned in 30 minutes, huge field of thousands of papers on nanotubes from 2D materials. But this comes, of course, on the background of the monolayers of molybdenum disulfide and the tungsten disulfide and many other layered compounds, which is much, much larger studies. And we are not dealing with that, but certainly our studies were the precursor because we were the first to work with 2D materials on the nanoscale. And our report from 1992 is basically the first report on nanostructures from 2D materials. And with that, I close my talk, and I thank you for your attention, and I'll be happy to answer questions if there are. Thank you.
Thank you, Professor Artene, for nicely presenting on the 2D materials. Thank you very much, Professor, for giving a detailed insight into the 2D materials and providing us the new knowledge and information about WaCl2, tungsten disulfide, and molybdenum disulfide nanotubes and nanosheets. Thank you once again, Professor Artene. Now the session is open for questions and queries, if any.
Are there questions?
Yes, I am looking for that. In the chat box, there is no question. Yep. Okay. I think we don't have any question from the audience. You have, in fact, you have explained the things in a very lucid and detailed manner. That's why I think we don't have questions and queries. Thank you, Professor Tene, once again.
Thank you very much.
Thank you, sir.
Now, next in line, I think I have next presentation from Burak.
So due to some unavoidable circumstances, he is not available at present.
Okay.
So we will not be having his talk. And I have tried to contact Professor Yulia by MOA, but she is also not responding.
Okay. So should I wait for some time?
Yes, sir. I think we should wait for 5-10 minutes at least. Yes, sir.
Okay. Right.
If Professor Yulia doesn't join in 5 minutes, then we will close the session, and all the other participants are requested to join session 2B or 2C if there are two, and we will be joining 2D session, which is actually the main session only. So the participants who have their presentation today in 2D, they will be joining this main session. It will be named as 2A or 2D, but 2D is the post one and 2A was the pre-lunch session. So all the other participants who are presenting in 2D will be joining this main session at 1:15. Once again, we are making announcement for Professor Julia by MOA. If she is available, she should make her presentation. Professor Julia.
Actually, the stipulated time is 12:30, and at Present it is only 11:35. That's why I think he has not joined. You can communicate through WhatsApp group, I think.
Yeah, we will communicate on WhatsApp group. So once again, I would like to thank Professor P.K. Shukla for chairing this session. Thank you so much, sir, for sparing your time and chairing the session. Now I request, sir, thank you so much. Now I request, yes, sir. Now I request all the participants who are here, we will be, if you have any presentation in this particular session, after lunch, then the session will start at 1:30 and you are requested to join at 1:15. If you want to listen to the presentation that are going on in 2B or 2C, they can join the breakout room. Participants who are here, the presentations of the sessions are over. And if we resume the talk of Professor Julia Baimova at 12:30, then we will connect again and we will inform this to you all. Meanwhile, you can join session 2B, 2C, which are running parallel. So all the participants, you are requested to join session 2B, 2C. And this session will resume at 1:15. Thank you so much, sir.
Thank you.
Yeah.